Today we shall study about kinetic theory of gases. Kinetic theory explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms or molecules. This is possible as the interatomic forces, which are short range forces that are important for solids and liquids, can be neglected for gases. For gases. The kinetic theory was developed in the 19th century by Maxwell, Boltzmann, and others. It gives a molecular interpretation of pressure and temperature of gas and is consistent with gas laws and Avogadro's hypothesis. It correctly explains specific heat capacity of many gases. It also relates measurable properties of gases such as viscosity, conduction, and diffusion with molecular parameters yielding estimates of molecular size and mass. Now the molecular nature of matter. Matter is made of atoms. An atom is made of very smallest particle like neutrino, etc. All things are made of atoms, little particles that have a round in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being stitched into one another. Canard in India and Democritus in Greece had suggested that matter may consist of individual constituents. The scientific atomic theory is usually credited to John Dalton. He posed the atomic theory to explain the laws of definite and multiple proportions obeyed by elements when they combine into components. The first law says that any given compound has a fixed proportion by mass of its constituent. The second law says that when two elements form more than one compound, force fixed mass of one element, the masses of the other elements are in the ratio of a small integer. To explain this, Dalton suggested that the smallest constituent of an element are atoms. Atoms of one element are identical but differ from these of other elements. Now, a small number of atoms of each element combine to form a molecule of the compound. Gay-Lussac's law given in early 19th century states when gases combine chemically to yield another gas, their volumes are in ratio of small integers. Avogadro's law or hypothesis says equal volume of all equal gases at equal temperature and pressure have the same number of molecules. Avogadro's law, when combined with Dalton's theory, explains Gay-Lussac's law. Since the elements are often in the form of molecules, Dalton's atomic theory can also be referred to as the molecular theory of matter. The theory is now well accepted by scientists. For many observations, we know that molecules constitute matter. Electron microscope and scanning tunneling microscope enable us to even see them. The size of an atom is about an angstrom, 10 to the power minus 10 meter. In solids, which are tightly packed, atoms are spaced about a few angstrom to angstrom unit apart. In liquids, the separation between atoms is also about the same. In liquid, the atoms are not rigidly fixed as in solids, but can move around. This enables a liquid to flow. In gases, the interatomic distances are in tens of angstrom. The average distance a molecule can travel without colliding is called the mean free path. The mean free path in gases is of the order of the thousandth of angstrom. The atoms are much freer in gases and can travel a long distances without colliding. If they are not enclosed, gases disperse away in solids and liquids. The closeness makes the interatomic force important. The forces has a long range attraction and a short range repulsion. The atoms at almost range attraction and short range repulsion. The atoms will attract when they are at low angstrom, but repel when they come closer. Behavior of gas. By gas equation, we know that PV over KT. For low pressure and high temperature, K is constant that varies with the volume of gas. K is proportional to the number of molecules, say N in the sample. We can write K barabar N a small k, where a small k is same for all gases. It is called Boltzmann Constant and is denoted by Kv. Now PV1 by T1, N1 barabar P2, V2 bata N2, T2 barabar constant Kv. If P, V and T are same, then N is the same for all gases. This is Avogadro's hypothesis. Now, that the number of molecules per unit volume is same for all gases at a fixed temperature and pressure. The number 22.4 liters of any gas is 6.02 × 10 to the power 23. This is known as Avogadro's number and is denoted by Na. The mass of 22.4 liters of any gas is equal to its molecular weight in grams at STP, and the amount of substance is called a mole. The perfect gas equation can be written as PV barabar mu RT, mu barabar number of moles and R barabar NAKV, barabar universal constant, T barabar absolute temperature, R barabar 8.314 joule per mole per Kelvin. So mu barabar M bata M naught barabar N bata Na. Now M barabar mass of gas containing N molecules, M barabar molar mass, Na barabar Avogadro's number, PV barabar kVnt or P barabar kVnt. Here N is the number of density, number of molecules per unit volume. Kv barabar Boltzmann constant is equal to 1.38 × 10 to the power minus 23 joule per Kelvin. So P barabar rho RT bata M naught. A gas that satisfies equation PV barabar mu RT at all pressure and temperature is defined to be an ideal gas. It is a sample theoretical model of a gas. No real gas is truly ideal. Now we calculate the pressure of an ideal gas. Consider a gas enclosed in a cube of side 1. Take the axis to be parallel to the sides of the cube as shown in figure 1. A molecule with velocity v, that's Vy Vz, is the planar, hits the planar with the parallel to the y-axis of the area A barabar L square. Since the collision is elastic, the molecular rebounds with the same velocity. Its y and z component of velocity if at the change in collision, but the x component reversed sign. That is the velocity after collision is minus Vx, Vy, Vz. The change in momentum of the molecule is minus mvx. So barabar minus 2 mvx. As the principle of momentum, conservation of momentum, the momentum imparted to the wall in the collision is 2 mvx. To calculate the force and pressure on the wall, we need to calculate momentum imparted to the wall in unit time. In a small time, interval delta t, a molecule with the x component of velocity Vx will hit the ball if it is within the distance Vx delta t from the ball. That is, all molecules within the volume Avx delta t only can hit the ball at time delta t. But on the average, half of these are moving towards the ball and the other half away from the ball. Thus, the number of molecules with velocity Vx, Vy, Vz hitting the ball barabar 1 by 2 Avx delta t into n, wherein the number of molecules per unit volume. So, total momentum transferred to the ball barabar q barabar mva half nva delta t 2 mvx into 1 by 2 nva delta t. So force barabar q by delta t and rate of change of momentum and pressure barabar force per unit area q by a delta t barabar n mvx square. It is equation number 1. All molecules in a gas do not have the same velocity, so p barabar n m vx square vx bar square, where vx bar square is equal to average of vx square. Now the gas is isotropic, so vx bar square is equal to vy square or vz square bar barabar 1 by 3 vx bar square plus vy bar square plus vz bar square barabar 1 by 3 v bar square, where v barabar a speed of the gas molecule, v bar square mean speed of the molecule. So p barabar 1 by 3 mn v bar square.